Okay, now let's go through the rules and let's see what they actually say. So before I show you the rules, I want to show you one way of writing the Leibniz notation. Remember that for Leibniz, we said if you have y, let me write, oh, sorry, I didn't pick my crayon. If you have y being equal to x squared, then you would say dy dx is equal to 2x, right? I'm about to teach you the power rule, which helps you know that it's 2x. Now, again, let's say you had something that says, now, let's say it says x is equal to t cubed. Then the derivative would now be dx. It means the derivative of x with respect to t, because it is a function of t. What we will be saying is, if I were to write it out, I'll do it like this, to say x is a function of t. In other words, it depends on t, okay? Normally when I write functions, what I put on my right-hand side is what we call the independent variable, okay? The independent variable, which means he is the input, he is the guy that affects the rest of the thing. And then this x is called the dependent. He waits to know what value t is. He is the dependent variable. So that's why when I write my derivative, I say the derivative of x with respect to t. dt means with respect to t, because x is affected by t. It is a function of t. So it depends on what t is. So when it's a function, it's like x is equal to t cubed, it'll be dx dt. Let me do one more, just so you master it. If I have, say, y is equal to 4 theta, then when I want to get the derivative, it will be dy d theta, okay? And this will be just 4. Now you differentiate. So I want you to get on notation that when I have a function, say y is equal to a function of something, here y is a function of theta, so I write it as y is a function of theta, okay? Y is a function of theta. It depends on theta. Now, this is Leibniz notation, the normal when you have a function, when you have something with an equal sign. But Leibniz doesn't end there. There's a way which we sometimes write, and this is the way that we do when we don't have it as a complete function, but we have it as an expression. So I've erased, and I'm going to just go back. I'm going to write it like this. Let's say I just had something that says x cubed plus 3x, and they said, please differentiate this. This is an expression. It has no equal sign. We don't know what x is going to affect. We don't know the output. We only know that we have x. So when I want to get the derivative of an expression, I just write it like this. I put my brackets and I say d dx will be now equal to, then I get my derivative. Okay? d dx of, so it'll be like d dx of x cubed plus 3x will be equal to, then you can put. Because we don't know the output, we just leave it blank. We know if it was y is equal to something x, we would say dy dx, derivative of y with respect to x. But now we don't know what the name of a function, we don't know what the output is, so our derivative of an expression, we just write it as d dx. Don't forget that, and it's going to help you know. So here when I'm doing the power rule, okay, I'm going to give you an example. I'm going to give you examples. The power rule, what does the power rule say? The power rule says that it will be using this to differentiate. So please make sure you know it. It is when you have a polynomial function or whatever, where you have powers there, okay? And I'm going to show you with examples. Here's what the power says. It says the most basic version. It says if you have y being equal to x to the power of n, then dy dx will be equal to, you bring the power down, so it'll be n, and then you reduce the power of x by 1. So it'll be n x to the power of n minus 1, okay? That is what the power rule says. So if I want to write it in one line maybe, so that for those that are writing, so that it makes sense, the power rule says if y is equal to x to the power of n, then dy dx, the derivative of y with respect to x, is equal to n x to the n minus 1. You bring down the power, then you reduce the power by 1. If we want to write it, if it was written as an expression, to say the derivative d dx of x to the power of n. This is another way of writing the power rule, but now we don't have y being equal to x to the power of n. We just have x to the power of n, and we are differentiating it as an expression. Remember, an expression has no equal sign or nothing. So we would say d dx of this is equal to n x to the n minus 1. That's another way of writing the power rule, okay? Why am I giving you this other form? I'm going to show you just now. It's still a Leibniz notation form. All right, now what we'll be saying is, on power rule, remember when we saw in the syllabus, if I take you back there maybe, just so that you remember, here they said you must know with constant multiples and with sums and with differences of functions, okay? That is, you must know the power rule in those situations. So now, what do I do? Well, I would say instead of having y is equal to x to the power of n, we now have a multiple. So it'll be like, if, let's say you now have y is equal to ax to the power of n, then what they now say it'll be is that dy dx, the derivative, would be equal to a is outside, and he will just multiply the derivative of x to the power of n. A is just a constant, so we just bring it outside to multiply. What is the derivative of x to the power of n? It would be n x to the power of n minus 1 from the power rule again. So this is the power rule, but now with a constant a. Another way to write it is to say d dx of a x to the power of n. We now have a constant a there. What do we get? We are going to get, this is equal to a multiplying d dx of x to the power of n. That is what it says when you have a constant outside. You just bring it outside. The constant is not part of the process. That is what it says, okay? So what it just means is I bring my constant outside, I differentiate the power rule the way I know it, then at the end I multiply by my constant. So it's going to be a is going to now multiply. Once the derivative of x to the power of n, it will be n coming down, then x is now to the power of n minus 1. You reduce it by 1. And you just get an and then x to the power of n minus 1. Now, this is when you have a constant. We are still on power rule. So here was case 1. Okay, I'll put the 1 here. This was case 1. And this was case 2 when you have a constant. And case 3 is for sums or differences. It is now saying, what if you have it say y is equal to ax to the power of n plus bx to the power of m. Maybe it now says minus cx to the power of, let's just leave it, minus cx like that. How do I get the derivative? This is now for things that are adding or subtracting or both. So here it's adding and subtracting. So now say dy dx will just be equal to, I differentiate one at a time. Okay, I differentiate. So this one would actually make more sense if we write it in the second form which you wrote it. To say d dx, the derivative of ax to the power of n plus bx to the power of m minus cx. This is just equal to, okay, this is now equal to what? It's going to be equal to the derivative of each thing, okay? Look, I don't have much space for my chain rule, but I'm just going to continue here for the product rule so that it makes sense. It will be equal to d dx of ax to the power of n plus, okay, this plus now comes, d dx of bx to the power of m, then minus this minus here, okay? Oh my, sorry for that. Let me just do this, remove this. Okay, then we say minus d dx of cx, okay? So, in other words, you differentiate one at a time. This is called a polynomial. In other words, it has many numbers. Nomials like numbers. So, how do you see the many numbers? They are separated by a plus or a minus sign. So, ax is one term. It's a multi-term thing. Bx to the m is another term. Then cx is yet another term. So, we have three things here, three terms. And when you want to get the derivative of this whole thing, you differentiate one thing at a time. That is what we use when we have these addition or subtraction. That's just what they wanted you to know. Now, that is it. We differentiate one part at a time. Then we'll be adding to the next part, whatever. Okay? We can differentiate one thing at a time. Now, there's something I want you to know on this one where we had multiples. You saw that we brought our multiple out, and then we differentiated the basic version of power rule, then we multiplied by the multiple at the end. Okay? This is the proper thing. But there is a shortcut. When you get used to it, there is a shortcut. You don't have to bring out the multiple, okay? Although you know that multiples don't affect your derivatives. Same thing, multiples don't affect your integrals again. They're going to multiply at the end, okay? It's not really part of the integral process. But here, what I want you to know is that, listen, what I want you to know is that when you have a multiple, there is a shortcut. So I could go just this way to say, if I want to get d dx of ax to the power of n, I bring down the power and it's going to multiply the coefficient. Coefficient means number in front. Remember, a is a number. It's a constant, which means it's a number. So I bring down my power, it's going to multiply the number in front. So it's going to be an, okay? And then the power will now reduce by 1. So it'll be x to the n minus 1. So that's what happens when you have a number in front. The power comes down to multiply it, then you reduce the number by 1. It's the same thing as pulling the power out this way and then only multiplying at the end. You see the answers are the same? An x to the n minus 1. So just know that, and you're done with your power rule. Now we'll look a bit at the chain rule and we will be done. What does the chain rule say and what is it for? Well, we'll look at examples of power rule and examples of chain rule in the next video, of course. But now, what does the chain rule say? The chain rule is for a multi-step process to get your derivative, okay? Derivative is the answer you get when you differentiate. It's a multi-step. That's what chain means, like a chain reaction, a reaction that happens in multiple stages. So in here, what it'll be saying is, you want to get dy dx, right? You want to get dy dx, but you can't get it straight away. It's going to have 2 steps. Now, if you want to know what happens in these two steps, the guy that goes on the top is always on the top. dy is going to be on the top. So we have a new guy that we're going to bring in, and it's called u. And we now will have a du. So du is going to appear 2 times here. Once is going to be at the bottom, and the other situation is going to be at the top. So if du is meeting dy, you see that my final solution is going to be dy dx. And dy is supposed to be at the top. So when dy meets du, is going to be dy du. Because dy is supposed to be at the top, so it's going to be on top of du. Then times dx is supposed to be at the bottom, so it's going to be below. So it'll be times du dx. And that is what the power rule states. It's just simple like that. The chain rule, rather, sorry. The chain rule states that dy dx, which is the one you want, you're going to have to get it in 2 processes. You have to get dy du, and you multiply by du dx. So you're going to have to get those 2, you multiply them to each other, you are going to get dy dx. It's like we'll be saying these du's cancel out and you get with dy dx. But in actual fact, you can't cancel them out. They don't cancel each other out, but it's like they do that. You kind of imagine it that way. That's how they cancel and lead you to dy dx, right? Okay, so that's what it is, and that is what your chain rule says. Okay, that is what your chain rule says. Now, you'd want to know which examples you do it. Let me just give you an example and we could call it quits. We'll look at more examples in the next video, of course. Or maybe let's just go through the examples in the next video. Goodbye for now. See you in the next video.